Okay, looking at your work here for number 12, you're looking decent. The graph is almost there. I see that you've graphed, let's call, for example, I think you're calling this graph B and this graph A. So what I'm seeing here is graph B. Note that it's greater than. So if we did test points, like 0, 0, 0, 0 is greater than 17, false. So we're shading up. The other graph, I think that's what you're showing up here. Graph A, that one has an intercept. Using the intercept method, when y is 0, the x is 14. And then similarly, when x is 0, y is 7.8 approximately. For graphing, we're not going to get much more accurate than that. So if we're going to graph those, for graph A, if you extend it out here would be 14, and then 0. Well, if this is 17, I'm having a hard time reading that, but if that's 17, then this would be 7.8, so it would look something like this. This graph would look something like that. But the big idea here, everything is shading up because it's all greater than. And then, of course, we're locked into the x-axis here. It's probably required, or within the x and y-axis, because we have the definition that x and y both have to be greater than 0. So I'll make these two different colors to make it a little easier to see. So what we're seeing here, shading up, the black line, equation A, or B, whatever that was, shading up. So the overlap would be everything in here. Okay, so now what we have to do is just say the question is asking us to maximize. So yes, we can look for corner points. We could say we've got a corner point right here where it hits the axis. We have a corner point where the two graphs intersect. We have another corner point there where it hits the axis. But we have to ask, are these points going to be the maximum? Well, our graph is continually going up. Our numbers are allowed to get as big as they want. It's not bounded. So if it's not bounded, our numbers can get gigantic. What would that do to the thing our objective equation? What would that thing do to the thing we're trying to maximize? Well, if there's no limit on x or y, is there a maximum? No, there's no max. So this is the one where they want you to look at it and just kind of use a little bit of logic and say, no max. Looking at the picture, these points, those are going to be a minimum. There'll be a minimum in there because it's bounded on the bottom end, but there's no max. So I think usually they want you to type in unbounded for that type of problem. Check the answers. It'll be in the directions. Then for number 14, we got a graph. I don't see our graph here anywhere. I see your equations, and your equations are right. Equation A, equation B, and then our objective. But I don't. It helps if you can spell. I apologize. I'm very sick. Objective. There we go. But I don't see a graph. So let's graph it and see what this. Okay, so I very quickly just found the x and y intercepts for both equations. So now I will call equation A. We'll graph that right here. Whoops, excuse me. Equation A right there. Now let's get green. Equation B in green. There we go. Now the big idea here is just that you see kind of which line's on top, which line's on bottom, and notice by your shading they're both greater than, or they're both greater than. So we are shading up like the last problem, because the A, if you use the test point, you'd see A would be shading this direction, B would be shading that same direction. So again, we are not bounded. But the question is the problem asking for us a max or a min? Well, because it's asking us to find the least, we want a min, we don't care how expensive things can get. We want to find what's the cheapest. So we just need to test our corner points. So our corner points are going to be right here. Now the good news, the reason I like the intercept method so much, this corner point, we've already found it. We know it's the y-intercept of the A graph, which is that right there. Now, we also need to worry about this corner point, so we can call it corner point 1, corner point 2, and corner point 3. Corner point 3 is right here. Now again, the nice thing about corner point 3, we already know it. That's the x-intercept of the B. So now the only other corner point we need to find and test would be where these two intersect, where line A and line B intersect. Now, one thing I find students miss all the time is why on earth did we do all of those solving problems that we did in chapter 2? And it's just because, look, we have linear equations. Let's throw this in a matrix, reduce echelon form, and let the calculator do it for us. So we're just going to go ahead and set up 60, 80, 140. Next one, 11, 21, 32. Throw that in the graphing calculator, reduce for echelon form, and let's see what. So when I do that in the calculator, I end up getting, and of course you could do it using Gauss-Jordan, or if you wanted to do it by hand, but the calculator ends up spitting out 0, 1, 1, 0, 1, 1, sorry, 1, 0, 1, there we go. Anyway, so of course we know how to interpret that at this point as x equals 1, y equals 1, but that's really an ordered pair of 1, 1. So therefore we know this point right here is 1, 1. So now we need to take all three corner points and test them in our objective equation. So we're going to take our objective, which you have written right there, substitute in the value of 0, 1.75, the value of 2.9, 0, and then the value of the third one, 1, 1, and we'll see which one gives us the least cost. So doing that for the first point, taking our cost equation, the objective, substituting in 0 for x, substituting in 1.75 for y, that gives us a cost of 91 cents. Now we repeat that with the next point, which was 2.9, 0. And that results in a cost of 92.8 cents. So far the one that's winning is the 91 cents because it has a lower cost, but we still need to check the point of 1, 1. That's where the two lines intersected. So when we do this, this is 0.32 times 1 plus 0.52 times 1. So essentially we just end up with 0.32 plus 0.52, which is going to be 0.84. So now we're just asking ourselves, which one has the lowest cost? Well, it's that one right there. So this is our answer. Whatever the variable x and y meant, I forget at this point. But the x value is 1, the y value is 1, so let's go find out what those are. Here we go. I believe you'll double check, but I believe what you did is you set the Gerber mixed cereal to be x and the Gerber mango tropical fruit dessert to be y. So you need one serving of each, one server of Gerber mixed baby, one of the dessert, and those servings are going to cost you a total of 84 cents. And there's your winner. Okay, I hope that helps with the two problems.